Let's formulate the Lagrangian for a simple pendulum. We start with a pendulum consisting of a mass m attached to a rigid massless rod of length L. We need to identify the appropriate generalized coordinate, which in this case is the angle theta that the pendulum makes with the vertical. The Lagrangian is defined as L equals T minus V, where T is the kinetic energy and V is the potential energy. For the pendulum, the kinetic energy is 1/2 mL squared times the square of d theta dt. This formula represents the energy of the mass moving along a circular path of radius L. The potential energy is mgl times 1 minus cosine theta. Here, we set the zero of potential energy at the lowest point of the pendulum. Therefore, our complete Lagrangian is the difference between the kinetic and potential energies. This formulation captures the entire dynamics of the system in a single scalar function. Now we apply the Euler-Lagrange equation to derive the equation of motion for our pendulum system. Recall from our previous section that the Lagrangian for a simple pendulum is given by the difference between the kinetic energy T and potential energy V. To apply the Euler-Lagrange equation, we first need to compute the partial derivatives with respect to theta dot and theta. Next, we need the time derivative of the first partial derivative. Now we substitute these expressions into the Euler-Lagrange equation. Dividing through by ml squared gives us the nonlinear differential equation of motion for the pendulum. This is a nonlinear second-order differential equation. Let's visualize the motion of a pendulum with a larger amplitude where the nonlinear behavior becomes significant. For small oscillations, we can apply a key approximation. When theta is small, sine of theta approximately equals theta itself. This approximation transforms our nonlinear equation into a linear second-order differential equation. This linear equation accurately models a pendulum with small oscillations. Let's visualize this case. The linear equation has a well-known solution in the form of simple harmonic motion. The angular frequency omega depends on the ratio of gravitational acceleration to the pendulum length. The amplitude A and phase constant phi are determined by the initial conditions of the pendulum's position and velocity. We can observe how the period of oscillation depends on the pendulum's length. A shorter pendulum oscillates with a higher frequency, while a longer pendulum oscillates more slowly. This demonstrates how Lagrangian mechanics elegantly derives the pendulum's equation of motion without directly using Newton's laws, giving us deep insight into the physical behavior of oscillating systems.